right, good evening, everybody. We have a lot to go over tonight, so we're going to try to dive right into it. Big Papa House, hey, good to see you again. Good, yeah, you're already watching the Nuggets for QoS. Good, so this will be a great conversation. Be sure to chime in with any questions you have as we go about it. So, first order on the agenda was me picking my drink. I couldn't decide between coffee and sparkling water tonight. Usually it's a sparkling water thing, but I was just cold. So I got coffee and I got sparkling water. So there we go. We're ready for whatever this night brings. I want to take a quick look at the, not the agenda. That's not updated. Wrong button. There we go. We want to take a look at what exactly Cisco has in mind for us to learn about QoS for the CCNA. And the CCNA, I'm not going to lie, this is a lot. And we're going to, like I said, we have a lot to cover tonight. And we're going to get as far in as we can. We might go a touch over. We'll see. It just depends on how quickly we make it through it. So don't hesitate to ask your questions as we go through. But we're going to start talking about just basic what the need of QoS is. And then we'll just kind of go systematically through what Cisco wants us to know. So we'll talk about marking. We'll talk about trusting, prioritization, shaping, policing. And this one right here, I will say, congestion management. That looks pretty innocent at the bottom of the list. But that is as I was preparing for this, I think I had as many, A through F subcategories under congestion management as I had under under QoS in general. So definitely a lot to talk about. Let me go ahead and pull up the whiteboard here, and I think we're good to go. So, as usual, again, chime in with your questions. Kind of got that agenda set that we're going to go through quality of service here, but like I've mentioned several times, we kind of got to roll with this too. All right, so why QoS and what is QoS? Let's just start with the absolute basics. So imagine, I will tell you this, from a home use perspective, there are days that I'm playing my video games online, right? Because I do that and I like to compete and I get very competitive. And of course, inevitably, while I'm in the middle of a match, I get this lag and this slowdown. And I run out to the living room and find out that, of course, not only are my kids streaming, but also, my other child is streaming on a tablet, and then maybe my wife is streaming on her tablet or phone, and we're consuming all of this bandwidth. And it's an online game doesn't require that much throughput. So if we think about it, if we have a small amount of data going through a single pipe, and then we also have a large amount of data going through, and this amount of data right here, let's call this time sensitive. It absolutely matters how long it takes between the time I push my button and the time that the video game registers to the server that I push that button. It's very time sensitive. Meanwhile, something like Netflix, which is constantly buffering, or any streaming service really that's constantly buffering, that, it doesn't really matter if this little byte right here gets through before all of these bytes do. And so quality of service, we apply this to the enterprise world, and we're not playing video games, at least we're not supposed to be playing video games while on the job. Usually the biggest place that this comes into effect is what we call voice over IP, or voice. So this would be, I'm picking up my phone on my desk, and it's an IP phone, meaning it's going through the network, not through the traditional telephone lines. Realistically, at this point, probably over 90% of infrastructures are built on IP telephony. So in all likelihood, if you're at your work and you're at your desk, you're picking up your phone, you're going to talk. Now, like the video game situation, talking on the phone doesn't require a whole lot of bandwidth. In fact, it's like kilobits per second. It's really minuscule. And so when we look at the fact that, okay, well, let's say I'm trying to have a phone call, but my neighbor is trying to upload or download a 20 gig file from the network share. Okay, same situation, right, as the video games and the streaming. It's the exact same scenario where I've got a small stream, again, just like this, that's time sensitive. It doesn't do you any good is, if I skip a word, I send, because that packet gets dropped or what have you, it doesn't do any good to resend that packet. It doesn't do any good if eventually it makes it to you. It needs to get to you on time. Otherwise, you start garbling like that, right? No, your Twitch is not messing up. That was just all for demonstration purposes. So we have this problem a lot in the enterprise, and it's not just voice over IP. It could be mission critical, traffic in the data center. vMotion can be a high priority traffic, but it can also be a heavy bandwidth. For those who have data center experience. So whatever the situation is, we need the network to be smart enough to say, hey, your higher priority traffic, you should go in front of the low priority traffic. So it's this concept of prioritization where we set priority levels and we say, okay, really mission critical data maybe is up here, and maybe we give it a number of 7. And then all the way down, or maybe stretching all the way up from 7 all the way down to 0, this is the highest priority, the highest of the high, and this is the lowest of the low priorities. And so network traffic that's going through the router, if the router can only pick one or the other, because of bandwidth utilization, well, we want it to pick the high priority traffic. That makes the most sense. So if we can configure our networks to be smart enough to do that, then boom, we're good. So here's the problem, because that's a very simple concept, right? Choose, small kilobits per second voice over IP traffic over, my, neighbor streaming Netflix on the job, whatever is happening. Executing it is actually very difficult. Our networks are complex, and we have routers and we have switches, and we have routers connected to routers, and we have routers connected to switches, which are connected to other switches, which are connected to routers. And maybe this pipe over here, this is huge, that's a 10 gig pipe, but this WAN circuit over here, this is like 500K. Well, probably not in this day and age, but maybe depending on where in the world you are. Maybe it's more like a 5 meg, let's just call it that. Say it's a 5 meg connection. That's pretty realistic for a branch site. So we've got all of these disparate connection types. We have different architectures because we have routers and we have switches. We even have Cisco routers and we have Juniper routers, heaven forbid, right? We're talking about CCNA after all. We've got Cisco switches. We've got different platforms. We've got Cisco Catalyst switches. We've got Cisco Nexus switches. And all of these platforms do QoS differently. And that can be one of the biggest frustrations when you're learning QoS. Really less about learning the concepts. Fortunately with CCNA, we just need to learn the concepts of QoS. And so we're going to spend most of our time tonight, really all of our time tonight, going through all the concepts of QoS. However, when it comes to configuring QoS, okay, configuring QoS on a router looks really different from configuring that QoS on a Catalyst switch. And believe it or not, configuring on that Catalyst switch looks really different from configuring on a Nexus switch. And that looks even different, by the way, than the newest Catalyst switches. They're different than the old Catalyst switches. And one thing that, before we move on here, just to help everybody understand that, is that quality of service doing these things with QoS, it requires tying into the hardware. Okay, there are these ASICs, we call them, application-specific integrated circuits. So when I've got a physical switch, I have physical chips inside that switch. And the way we queue traffic, the way we manage traffic queues and such, which we're going to talk about tonight, the way that all happens is usually built into the hardware. Meanwhile, routers, by the way, these are software machines. So routers, the good news about routers is that they're extraordinarily flexible. We can do almost anything we want from a QoS perspective on a router. But when it comes to switches, it's very reliant on those underlying ASICs. And again, the ASICs that were developed in old Cisco switches are different from the ASICs that were developed for new Cisco switches, which are different than the ASICs that are developed for the data center for those Nexus switches. And this is why the implementation of QoS can be such a nightmare for all of us, unfortunately. So just understand that, that when it comes to configuring it, there will be some hurdles there. But regardless, with CCNA, fortunately, we don't really need to know too much about that. We simply need to understand a lot of the concepts. So the first concept that we need to understand is when way back, I should step even further back than that, but way back probably in the 90s, I don't really know what year it was, there were two different theories on how to do QoS, okay? So when we think about it, what did we used to have We probably have talked about this a little bit, right? When you look at circuit switched networks versus packet switched networks, if anybody took their CCNT, if anybody took their CCNT, ICND1, you probably studied that, right? The concept of a circuit switched phone is like old telephones, right? Where if I get on the telephone here, I have a dedicated circuit to somebody over here. And networking, the concept of networking was, well, we could do that. Like every time a computer needs to talk to another computer, I get a dedicated line to that other computer. I mean, that was modems, basically, right? Going over the phone lines. But as we evolved our concept of exchanging data, we realized that a packet switch network works a lot better. Because in the phone scenario, yes, this is good because I have dedicated bandwidth, but this phone right here wants to call this guy, and he's getting something none of us have heard for a decade, is a busy signal, right? Because we have no available circuit for that third telephone. Meanwhile, in a network, this concept of packet switching says that, hey, you know what? Even though these three, let's say these two computers are talking to each other, this computer needs to start talking to this computer as well, and that can all happen because we're sending packets now, and these packets can get interspersed and interweaved with each other so that the destination computer can receive both communications at once. Okay, so this is circuit switched versus packet switched. And a concept that we need to understand is that QoS theories, we have two different theories around QoS, and we actually had protocols that were developed around both of these. The first one resembles the top diagram with the phones, the circuit switch concept. We had a protocol called the Resource Reservation Protocol, which is RSVP. And RSVP, really, what I should have said first, it belongs to this theory of integration. Integrated services. There we go. So we have integrated services. And the theory is that, okay, so this computer needs to talk to this computer, and I'm going to reserve so much bandwidth. Let's say I need 5 meg of bandwidth. Well, in order to reserve that traffic, I go to this router, I send that request upstream to the router, and it either says yay or nay. Yes, you've got 5 meg. Yes, I've got that much bandwidth or not. And then it proceeds to send it to the next router, and of course it gives a yay or nay, and it sends to the next router. And if, indeed, I get approval through the whole process, I can get 5 meg of guaranteed traffic through this network. These routers will lock down that 5 meg and give it to nobody other than that original computer or speaker, the source. That's the concept of integrated services. Then we have switchboard operators. Yeah, you kind of takes you back to that concept, right? I mean, that's what the routers are doing, right? It's like, okay, clear. Meanwhile, we have this other concept, and this will probably sound a little bit familiar. It's called differentiated services. And the reason it might sound familiar is because we're going to talk about something tonight called the Differentiated Services Code Point, or DSCP. And anybody who's spent a little bit of time studying QoS is going to know at least what the acronym DSCP is referring to, which is just to say that it's referring to QoS. Differentiated services is similar to this packet switching concept, which is simply to say that I'm going to provide bandwidth guarantees that any packet flow can take advantage of. So I kind of set these up already throughout the course of the network, and I say that, let's just say voice over IP can get 5 meg of throughput throughout this network. So by guaranteeing that VoIP has 5 meg, now my phones can take advantage of this, even though this phone only needs, I mean, again, we're talking kilobits per second, but let's just say it's like 0.5 meg or something like that. Well, in theory, I could have 10 of these phones now, because if each one is taking up 0.5 meg, I can continue to attach phones, and they'll just consume what they need. Versus think about that RSVP situation. What happens if I add a second computer in here? And this computer, let's say it's only using 1 meg of that throughput. Well, it's reserved all 5. So in order for those routers to guarantee that it gets 5 meg of that throughput, it can't share that 5 meg with anybody. So if we back up and we kind of take a look at this, which one of these two scenarios is better for the individual, machine? Well, circuit switching is way better for the individual, And RSVP, integrated services, that is the same situation, right? It's great for the first computer to get that reservation, which is why, by the way, we have this protocol. And we, believe it or not, you can still configure this protocol in a lot of cases. It's not really used, just fair warning. We don't use it anymore. But we do have a protocol and a whole architecture built around this, because every now and again we have this same concept of, yeah, Big Papa, yeah, you got it, circuit switch. The same concept of just needing to guarantee bandwidth. But what is better for the overall utilization of the network? And that would be both the packet switching, which of course is why we landed with packet switching, and differentiated services is going to be the same way. It's better for the overall network. It's, not one computer, one speaker is going to win out over everything. So these are the two concepts that we're going to need to understand that on some level. I would expect a question on this with the CCNA. You just never know for sure what they're going to ask. I would say that if you're going to take the CCNA after the new date in February, it's less likely they'll ask about RSVP, but on the current CCNA, I would say it's fair game for sure. It's hard to say that with the exam blueprint being as vague as it is, but just this general concept of integrated services versus differentiated services is sort of a QoS 101 conversation. So let's dig in. What are we digging into? Actually, what are we digging into? Let me check my notes here. We're going to talk about marking. That's right. Okay, so section A of the QoS conversation is marking. Now, we just gave a scenario. Hello, there we go. We just gave a scenario where we have a series of routers and we have some device that's trying to communicate to the rest of the world, and these routers are going to need to apply policy to that traffic. And so the question is, how does that router, when it receives the traffic, how does it know how to treat it? Okay. The concept is that we have to mark those packets in such a way that the router can receive the packet, basically tell how it's supposed to treat it. All right. So we can mark packets in certain ways, usually with a tag of some kind. So if I've got two different computers here, for example, and they're both communicating, we have two different streams going, and let's say I tag this packet with a 5, and the higher number is the better in this case. So we'll say, okay, so this is a 5. That's a pretty good priority. Let's say it's out of 7, and you'll see why we're talking using these examples, because realistically 0 to 7 is a pretty common range for QoS values. And let's say the computer up here has a value of 2. So there's a lot of different concepts we're going to get to when we drill more into the QoS as we go on tonight, such as, for example, let's say this 5 stream is actually a pretty big stream, and now we've flipped it backwards. Right now Netflix is the high priority and the video game is the low priority, even though it doesn't need much. So if we're constantly sending that traffic of 5, what do we do with the traffic of 2? Do we drop it? Do we occasionally let some traffic through on 2? I mean, we'll talk about kind of our options around that, but that doesn't have anything to do with marking, fortunately. The concept is simply we're going to eventually configure policy against something. What are we configuring it against? Well, we're going to configure that policy against the marked packets. So we've got a lot of different ways of marking packets. Unfortunately, we truly have 3 different ways of marking packets that we have to go through tonight. And this is where QoS gets to be a pretty big conversation. All right. I like that. Flip a coin if well, just random, right? Just randomly do it. Believe it or not, you're not far off from the truth. We're going to talk about some weighted random early detect later, and yeah, we definitely get into some coin flipping, so to speak. So, all right. So, yes, okay, IP precedence. IP precedence is the first method that we have for marking packets. So this was actually chronologically also the very first way that we had to mark packets as well. This is taking a section of the IP header, specifically 1 byte. When IP was developed, we had what we called the type of service byte. That type of service byte, a byte is 8 bits, so we have 8 bits. And the concept was this: IP precedence. We said, okay, we're going to take, let me just go ahead and clear the screen on this because I think we're going to need all of this real estate. We'll choose a more appealing color than yellow. All right, so IP precedence, the IP header, we took a byte, we called it the type of service byte, which again is 8 bits. Now, what IP precedence did was it really took the first 3 bits. So let's just do this. So 1, 2, 3, 4, 5, 6, 7, 8. Okay. So we've got 8 different bits within this byte. And IP precedence took the first 3 and said, we're going to categorize our traffic this way. All right, with 3 bits, and those can be all zeros through all ones. So with 3 bits, 2 to the 3rd power gives us 8 values. This is why we've been using 0 to 7 as the example. Because if these are all 0, 0, 0, 0, that's an IP precedence value of 0. If they're all ones, binary 1, 1, 1, well, that would be 7. So 0 to 7 is our min and max range. So IP precedence gives us this range of 0 through 7, and it allows us to mark our packets. Now, who's marking the packets? Usually, it's a mix of things. So like an IP phone, for example, it's going to mark its own packets. If I wanted to, I could download firmware to my computer, and I could, usually built into Windows, there's not a whole lot of options there, for example, but if I download custom firmware, then I can do whatever I want. And so I could, on my machine, I could set my own IP precedence values. Usually not a good idea, because then if I'm marking everything with, like, let's say a 7, well, then that's telling you that my Netflix traffic is more important than those routers trying to communicate with one another. That's bad news. So we'll talk about trusting here in a little bit as well, whether we want to trust those values as they come in. So yes, the end device can definitely set its own value. Most often, the best place to tag a packet, to mark a packet, is, so let's say we have a machine and maybe even a phone connected to the switch. The best place to configure that marking is right here on the switch port. So we typically want to get onto the edge switch as close to the client as we can and mark the traffic there. So this does take intention. So what kinds of traffic do we want to tag? I mentioned voice a few times. Video is another really good one, by the way. When you get into it, like in the data center, again, I spent a lot of time in the data center. iSCSI is storage traffic. We absolutely want to prioritize iSCSI. I mentioned vMotion as another one. It just depends on your environment. Typically, there's not a lot that you need to mark outside of voice and video, unless you're inside the data center. So those are definitely the 2 main ones. You can actually go a step further and say, okay, well, we've got video, voice, and then video, and then best effort we call it, which is kind of everybody else, and then maybe create a scavenger class. That scavenger class would be like, you don't even get as good priority as best effort. But the kinds of things that you don't need that much control. And so if you find out that, hey, we've got this mission critical application, it absolutely has to communicate regardless of anything else, well, then you could throw go to that server, right? Maybe it's a server communications. You go to that server switch port and you say, hey, everything on that server, let's say we have a server hanging off over here. So everything on the server, let's mark that if let's say if voice is a 5 and video is a 4, and believe it or not, voice actually uses 3 as well, typically. So voice, what we call voice control traffic, uses 3. Well, we've got 2 empty, so let's make that our application. Whatever that application is going to get 2, and so we tag all of that traffic with a 2 as it comes in. So we want to tag or mark that traffic as close to the edge as possible. That is certainly something they could ask on the CCNA. They might show a network and say, where should the tagging occur? And if it's sourced from this server over here, then the answer would be the nearest switch port, ideally, is typically the answer for that. So IP precedence was good. We decided, though, in some environments, 8 values isn't good enough. And so that became a problem. I need to erase this because I'm going to use that space. We'll say IP precedence come on, there we go. 0 through 7 is all we could get with IP precedence. So we got 8 values. By the way, even further to reduce what we have, 6 and 7 are reserved in most cases. 7, every time a router sends a packet, like an OSPF packet, EIGRP, some kind of control plane traffic, it's usually marking it with a 6 or a 7. And so I believe routing, I did not look that up. I can't remember now if it's 6 or 7. But either way, yeah, I mean, look that up when you're studying for your CCNA. But we can't use 6 and 7 in a network in most cases. So really, we're talking about 6 values. And 6 might not be enough, because just me rattling some random things off here, in a lot of environments, we're going to have those things. And there's 4 of our 5, right? Because that best effort class is going to be 0. So we're already using 0. We're already using 3, 4, and 5. We need more values than this. So this is where the concept of DSCP comes in. So DSCP was an expansion of IP precedence. DSCP, I already mentioned it, but it stands for Differentiated Services Code Point. And it was simply built to give us more bits so we could mark things more granularly. So now that we have 6 bits, well, 2 to the 6th is 64. So now we actually, with DSCP, we can go from 0 to 63. That would be 64 total numbers, right? Big Papa House. If I understand correctly from earlier, the closer to the end device you can start the marking, the better off it is. Yes, thank you for the clarification. You want to mark traffic as close to the source as possible, generally speaking. All right. So DSCP. So that's great. Now we have 64 different classes. Now we almost have the opposite problem. Now I've got so many numbers, I don't even know what to do with them all. And so the industry came up with some helpful, we call it helpful ways of providing some standardized values for us to follow. And even though it's helpful, it's also kind of obnoxious, because now we, studying for the CCNA, need to really study all of that and try to keep up with it all. And it can be a big pain. But fortunately, it's not too bad. So but we do need to walk through this. So first of all, what they do is they take specific numeric values and they assign letters to them. Call it assured forwarding is the word that is the word that they used. So let's say DSCP values. Let's just make one up here. Let's say we have a DSCP value of 10. All right. So as DSCP value of 10 would be 1. Actually, let me change colors here to make it more clear. And you know what? I'm going to make this a new layer so we can maybe very easily wipe and erase these. 1, 0. That's not very clear, is it? Hold up. I'm going to try a different color. There we go. That's clear. 1, 0, 1, 0. Okay, that's a 10. So this concept is taking the IP precedence value here as one number and the DSCP values as another number. So if I look at it from a binary perspective, this right here, 001, is simply binary for 1 decimal value, right? And 1 is 1. That's good. All right, so we're calling this assured forwarding, AF, 1, and then what's the DSCP value? Well, that's a 2. That's just a 1 bit here, 2 bits here, 4's there. So we have a 1 in the 2 spot, so we'll put a 2 down. Okay. Actually, you know what? Hold up. Mouth was moving faster than my brain on that one. We actually are only looking at these 2 bits. I apologize for that. So when we're talking about assured forwarding, for whatever reason, and believe me, I've looked all over to try to figure out at what point it became this way. For whatever reason, this bit right here is always 0. I think it might have even been, I don't think it was in the original RFC. So if anybody has some really cool insight into why that's always a 0, then let us know. But either way, it's always a 0. So really, when we're talking about DSCP, we can only change 5 bits. Now, our values do still go from 0 to 63 because, well, technically 62, right? I mean, with that being a 0, we effectively have all of the even numbers available to us and none of the odds. because we can't have it all be 0 and then a 1 at the end, right? We can have it all be zeros, and then as soon as we put a 1 here into this spot, well, now it's 2. And so that's as granular as we can get. So we technically only have 32 values, 0 to 62, with all the evens. I know it's weird, and I wish it was more straightforward than that, but the reality is that this is what we have to know. And so this assured forwarding actually comes into play because when we were talking just a moment ago about, okay, I'm going to call this AF1 because IP precedence is set to 1, but I'm not looking at all 3 bits. I really am only looking at those 2 bits. And those 2 bits, if I just take them straight as they are, well, that's a 1. 0, 1 is 1. So this is what we call assured forwarding 1-1 or assured forwarding 11, however you want to say it. So AF11 is supposed to mean something, but it doesn't really mean much yet. Let's do a few other examples. Let's say that we have the same IP precedence value, but now this bit becomes a 1. There we go. 1. Ha. All right. So what's that? Well, again, we take the same process. Assured forwarding, the IP precedence is 1. And the other 2 bits, 1, 1 in binary is 3. So that's assured forwarding 1, 3. So now we've talked about 2 separate DSCP values. AF11, you remember that what the decimal value was for that we said? It was 001010. That's binary for 10. So that'd be a DSCP value of 10. AF13, we added, what bit did we change, right? We changed this one right there. So that's the 4s. So we technically just added 4 to that value. So AF13 is 14. At the end of the day, this is only a DSCP decimal value. I mean, if I just told you, hey, this application is using a DSCP value of 10, well, you could go into your Cisco device and configure certain policies against a DSCP value of 10. Keep in mind, this is all part of the markings conversation. We're simply talking about different ways of marking our packets. I mean, ultimately, the router is just going to look at all the 1s and 0s. So this is all just from a human perspective. So when it looks at the 1s and 0s, ultimately it sees a decimal value of 10 versus a decimal value of 14. And if I configure that versus configuring the Cisco router, and I can get onto the Cisco router and say AF11, it will know what that means. It's just like a human word for 10. So what's this mean? Why are we even talking about all this AF stuff? Well, the reason for that is because, again, the industry tried to put some organization around DSCP values. So as they laid this out, they said, okay, well, we're going to have AF11, actually, you know what? I'll just write it out this way. AF12 and AF13. And then AF, because the IP precedence value can go up, we're going to have a 21, a AF22, and AF23. Now, could they have done an AF20 or an AF10? Yes, they could, and they did, but they called it something else, which we'll talk about in a moment. I know, it just keeps going on and on. So as we do this, there are actually 3 different levels of this AF. Wait, did I say 3 or 4? I can't do 2 things at once. There's actually 4 levels of this. And I'm writing them all out here. And again, as obnoxious as this is something that we absolutely must know for the CCNA. So the 12 different AF values I just wrote out, these all correspond to decimal numbers. Again, AF11 corresponds to 10, like we talked about. 13 responds to 14. We could probably guess that 12 corresponds to 12. Yeah, actually, it does. And so as we move down the path, we could actually calculate out which one of, which values are assigned to which numbers. Now, there is a way to do this. I'm going to go ahead and tell you right now. It's this, call it an algebra equation, right? It's 8x plus 2y. Okay? So if you have AF, if you're given AF xy, which again, fair game on a Cisco exam, right? If they say, here's AF32, what decimal value or what DSCP value corresponds to AF32? Well, memorize this algebra equation because it makes it very straightforward. AF32, I plug the 3 in here, so it's 8 times 3 plus 32, 2 times, so this would be 2 times 2. So that's 24. Oh, Man, okay, I just remembered I have... Oops. All right, this is what I try to get, or what I get for doing this live. I tried to move my headshot. So sorry about this. I am writing underneath. Let me just I think I can go full screen here for a second. I think I can. I never made that. Okay, so I never made a scene for that. All right, let me just move myself over here. I know it's looking weird. There we go. All right, now I'm over here. All right, I apologize for that. Okay, so hopefully it's updated. Let me know if you can see it now. Yeah, Shira, I apologize for that. And it looks like you guys have been warning me for a while now, so sorry. Okay, this is good now. Okay, so I'll quickly rehash what I was saying. So this, let me change colors. Here, there we go. Okay, so this algebra equation right here is what you're going to want to memorize, 8x plus 2y. Because Cisco on the exam might give you this. They might say AF32 is what the example I was trying to give, right? So if they say AF32, what decimal value does this correspond to? You can very quickly figure it out if you have this algebra equation memorized. Otherwise, you're going to have to kind of reassemble this, from a bit perspective and be like, oh man, AF32, I know that that's a 0, 1, 1, and then a 2 is... You'll have to memorize it and take it all back to binary. But if you have that equation memorized, you can just skip that. Now, the reason this binary equation works is because this is the 8ths bit right here. So we're taking our IP precedence value. What do you say? 3, right? This 3. And we're multiplying it by the 8ths bit. And then the same thing here. This is the 2's bit. Or the 2's column, or however you want to describe it. So again, think binary math, right? We have 1, 2, 4, 8, 16, and 32. We're just making the 8 and the 2 the significant part of this equation. So that's where the algebra comes from. I don't want you to simply assume that is like, or I don't want you to memorize an algebra equation and not know where it comes from. There's method to the madness here. And so what I started to write there at the bottom is that, okay, so let's say we were given, again, AF32. I would simply take 3 times 8, which is 24, and then I would do 2 times 2, which is 4, so it should be 28. 28 should be the answer. All right, so I highly recommend, again, just committing that to memory and understanding how to bring the AF values back to a decimal value. I actually have a, let me see here. I've got a separate PDF document I wanted to share. So this is a Cisco document that honestly I Googled searched for it, Cisco and I think AF values or what have you, because I just wanted to see where Cisco laid them out, because they usually do somewhere, right? And so as we scroll down here, we start to see, actually, let's double check our number. What do we say? 32 is 28. All right, we got it right. So here's the binary over here. And you see that they've got the first three bits in bold. The second 3 bits would be the DSCP values. Here's the decimal value. Here's the AF. And then from there, just, these are, believe it or not, I did skip this part. A lot of IP precedent, all the IP precedence values have a value also associated with them. For example, IP precedence of 0 has the, it's called routine traffic. And so it kind of works its way up the list. We don't necessarily need to worry about that, but, just add it to your study list, I suppose. All right. So I wanted to share that with you just to show that this is not something I'm making up. This is something that is very industry standard, and we need to understand this. Like I said, routers you can tell a router to pay attention to AF11 traffic as a marking, and it will look for DSCP values of 10 because it's smart enough to do that. Now, I did mention earlier, let me just go ahead and flip back. We mentioned earlier that, okay, so why is there not an AF10? Why is there not an AF20, a 2.0? Well, those are actually special values as well. And let me clear the screen here. Get back to this. All right, so when we're talking about, oh, did I not give myself a new, there we go. One day I'll figure out maybe there's a better art program out there. All right, so let's say that we've got the value of 0, 1, 1, and then 0, all zeros. Okay, so this, in theory, if I could just kind of construct the AF value myself, I could say, okay, so this is an AF, IP precedence is a 3, DSCP is a 0, so this would be AF 30, which sounds good, and that would technically be correct, except they give it a different name. We call this, and I believe it stands for Common Services. I'd have to look up what CS means, but we call this CS3. And I mean, I don't know why they did it that way, but they did it that way. And ultimately what this is saying is, guess what? This is the exact same thing as saying IP precedence 3. Because my IP precedence bits are set to 3, my DSCP values are irrelevant. They're all 0. And so understand that when we're dealing with DSCP, CS3 is equal to simply using those first 3 bits. It would be lovely if IP precedence being legacy was so far gone that we wouldn't need to worry about IP precedence anymore, but unfortunately it just simply isn't the case, especially when it comes to Cisco exams. They really want us to understand the difference between those 3 DSCP bits and those 3 IP precedence bits. Okay, so up next, we're going to, oh, you know what? I almost skipped over a very important part. All right, there is actually 2 things. All right, 2 more things with this. One of these things, I'm going to bring back the old here. All right, so one thing we need to understand about the assured forwarding concept. As we go down, darn it, I didn't pick my layer. There we go. As we go down this list, so as we go from assured forwarding 1 to 2 to 3 to 4, the priority goes up. And you'd think, if you're like me, because I used to think this, you'd think that as we go this way, it also goes up. So AF11 is lower prioritized than AF12, is lower prioritized than AF13. But unfortunately, when they designed the spec, and the whole reason why, they kind of got away from this, but when it was originally designed, it was that this bit right here, and I was getting busy, but that 5th bit was supposed to refer to how likely it was to drop. And so that when they translated that over to DSCP, these assured values, essentially, as they go up, it's the more likely that they will drop, that they will get dropped. So in a weird way, you actually are going down. Whoops. There we go. So we're actually lowering, if I can draw this backwards, we're going more priority to the left and more priority down. It's really bizarre. And it takes a little while to wrap your brain around that, understood, but just take it for what it's worth. Now, do routers, class selector. Oh, thanks for looking that up. OGIT, Keith. Hey, thanks for coming, Keith. Good to see you. Thank you for chiming in with that. All right. So, so as the number goes up, that's more likely for them to get dropped. So let's just keep that in mind. Oh, I remember now. I got distracted by class selector. What I was saying. Do routers automatically make it so that they're going to be more likely to drop AF13 traffic over AF11? The answer is no. All of this is sort of how the industry views things, and they want to standardize things. So, if you as an IT person, you start off with one company and then you go to another company and you're bringing your knowledge with you. They kind of want the industry to be standardized around these same concepts. But at the end of the day, when you've got 3 routers or what have you in a row, every router is going to be treating this traffic as you locally configure that router. It's one of the other pain points of QoS is simply that you've got to have your entire network be cohesively configured to be deploying this, to be applying the same policy to your traffic. So when it comes to the AF concept, there's nothing that, I could configure my router to make AF13 the highest priority traffic and to drop everything AF41 as soon as something AF13 comes in. I could do that. I have that control because I can configure that. But obviously that goes against the way the industry kind of wants us to, and so just be aware of that. The other concept that I almost skipped out on, I want to go ahead and pull the We'll just do one more layer here. Is this concept of expedited forwarding. Okay, so we have one very special value. It's called EF, expedited forwarding. If it had an AF equivalent, it would be AF53. Because what we're going to do is we're going to put a 5 in here, 101, and then we're going to put a 3 in there, 11. And if my math is right, this is going to equal 46. It's a decimal value of 46. What this is it's supposed to be the highest priority traffic that we configure within a network. Now, I already mentioned that, routers speak at that, CS value of 6 or 7 or what have you. I mean, they're speaking at a higher level. We have to have those reservations. But within a network, I want to make 46 the absolute highest priority of everything. Which is interesting because, I guess I'll just leave that alone. All right. So when we configure our routers, we have the option to apply a marking to packet types, and this 46 is usually synonymous with, again, that voice over IP, because there aren't a lot of networks out there that have anything on the network that's more mission critical than voice over IP traffic. VoIP is very, very important. It's a very high priority. Lives could be at stake, literally, right? Like if you need to pick up a phone and call 911, those phones have to work. They have to work well, and also, even though on the one hand they're very, very, they're tied to the human health. It's also the first type of traffic if you experience even a little blip, then it's going to be painful. I mean, I was on a phone call earlier today, and the person on the other end of the line I know I'm at home, so I've got great Wi-Fi service because my phone's on the Wi-Fi. Wherever they were was miserable. And the funny thing is when I think about it, I was probably getting about 80 to 90% of what they were saying. And 80 to 90% seems like it's pretty good. But I tell you what, again, that 10% or 20%, whatever I was losing was enough that I could not understand what they were saying. And eventually the call was dropped. And so that's why I say it's like, even just a little hiccup can make it so we can't communicate. Now, we mentioned video as well. Is video or voice more important? Because you'd think, well, video, that's very important too. If you're having a video call, you have to be able to see each other. But I tell you what, if the video goes out a little bit and the voice stays, does it still work? Yes, I can continue, even though it's the quality is low and I'm annoyed that the quality is low, we are still communicating. What if it's the opposite? What if the voice is a little hiccupy and the video is immaculate, it's perfect? Well, I can't communicate with them. So video actually is a lower priority than voice for that reason. All right. Moving on, I think now to, remember we talked about 3 different types of markings? So we've covered 2. We've covered IP precedence and we've covered DSCP. I'm looking if there are any questions. I don't see any questions jumping in here. So if you do have anything about IP precedence, DSCP, any of the assured forwarding, expedited forwarding stuff, be sure to chime in with the chat. We'll try to address it live. Now we get to have the conversation for the last value, or the last form of marking that we have, and that is called class of service. Class of service takes us away from IP. So everything we were just talking about was in the IP header. Okay, if I have traffic that doesn't have an IP header for whatever reason, it's pretty rare in this day and age that we have any non-IP traffic, but every now and again we can have that, especially in the data center and such. Then we can't use those values, right? We can't do IP precedence, we can't do DSCP because we don't have an IP header. Well, that is a rare situation. The more common situation is that we cannot use class of service, and here's why. Class of service happens in the Ethernet header, and unfortunately, when Ethernet was devised, it was not given this concept of a marking. We had no way of marking it. And that created 2 problems. One, sure, class of service was certainly a problem, but another problem that had to be solved was, hey, we've got all of these networks. We want to kind of virtually segment them, virtually segment the LANs, right? Virtual LAN, ringing any bells? So when we have the Ethernet header, we had no way of marking for class of service, and we had no way of marking for VLANs. And so as we know, when we're talking about, because we're studying for ICND 2, in ICND 1 it definitely was covered, we have two switches, and let's say I have a host in VLAN 10 and a host in VLAN 20, and these two hosts need to go across that same link. So when this switch receives those packets, how does it know which VLAN the traffic I'm receiving is? Well, kind of in the same way we're talking about with QoS, we have to mark that traffic. And the way we mark it is with a VLAN tag. But again, Ethernet header doesn't have a spot for VLAN tags. So what they did, I wasn't around, but what the industry did was we carved out a section, well, not carved out, I'm sorry, that's the wrong way of saying it. We actually injected we injected a section of additional header that gets added into the header on certain links. And so what we did was we added the ability to do the VLAN tag as part of that. That's cool. And we also got 3 bits for what we call class of service. So the VLANs, they got the bulk of it, right? There's like 12 bits on the VLAN tag. We can have up to 4,096 VLANs. It definitely got the lion's share of the bits. But the class of service, we got 3 bits, and guess why? Because IP precedence has 3 bits as well. So we can start to align our layer 2 quality of service, which is what Big Papa House said, right? Class of service is layer 2. We can align our layer 2 QoS with our layer 3. Now, it does take a little while to read. It's like MTU. If you ever had an MTU conversation, it's like, oh, there's layer 2 MTU and there's layer 3 MTU. And it takes a while to understand the differences and when one comes into play and when the other one comes into play. Same thing with this, unfortunately. It'll take a little while to kind of see into this concept and understand this. But one of the biggest things we need to understand is that the 3 bits for class of service only show up when that VLAN tag shows up. So here's the pop quiz for you. Where in the network are my VLAN tags? What types of link? I'm gonna take a sip of coffee while you think about that, because I haven't even had a sip of my coffee yet. And as expected, it's not the hottest anymore. All right, I'm seeing some options coming here. Trunks, yes, absolutely. Trunks is where those VLAN tags exist. So if I were to set up a network that has, let's say, two switches, and we're not trunking here. Okay, so this is what we'd call an access port, and I bring my traffic in, and I do what I'm supposed to do, and I tag this traffic with a CoS of 3, or whatever value I want, and that packet ends up getting sent across this link. That CoS tag of 3 was just lost. Okay, so my end-to-end QoS policy is going to be fragmented, because as soon as I hit a link that doesn't have the ability to tag traffic, the ability to tag VLANs, I also lose my ability to tag QoS. Okay. For the most part, we rely on layer 3, I almost said MTU. We rely on layer 3 QoS because it's end-to-end. IP, the IP header is for the most part going to stay the same, even though, yes, it gets torn down and reconstructed. Actually, no, it shouldn't get torn down and reconstructed as it goes from hop to hop. But that's the point, right? It should persist all the way, and so that tag should be kept all the way down. Scratch my tags, I'll scratch yours. And so one fun thing, by the way, about Cisco tagging and such on switches, it's very intelligent around some of this. So it can receive a CoS value of 3 on the Ethernet frame, and it'll recognize that, and it'll actually translate that over and put it into the IP header for us, and vice versa. And so it just depends on the model. Again, that's one of those diving into the weeds conversations. Not expected for us to understand that on the CCNA. But understand class of service, layer 2, 3 bits, which means, again, 0 through 7, right? That's wrong. There we go. 0 through 7. That's what we can do with class of service, layer 2 QoS. All right. So yes, generally speaking, we want to align with the layer 3, but generally it doesn't matter. So the question though is when we define our policy, what are we applying that policy to? Because I can match against IP precedence, I can match against DSCP, and I can match against QoS. And so it's whatever I'm telling my device to match against that's what it's going to pay attention to. And so a lot of layer 2 switches, by the way, can't match on IP precedence because it never looks at the IP header. So keep that in mind. If we need it to be able to tag on, to apply policy to a QoS value, well, then we need to make sure those QoS values exist and that we're trunking everywhere we can. Okay, so that is QoS. All right, so we are nearly done with the first hour. We've got 55 minutes in, and we are done with Section A. But I knew Section A and Section F are definitely the long ones, and we are going to burn through the rest a little bit quicker. So let's go ahead and dive into Section B, which is actually device trust. So this is going to be the fastest section because it's not too complicated, but we do need to understand it for the CCNA. So this concept is this. We have the example I gave earlier. I'm sitting here on my machine. I'm getting frustrated with my Netflix or whatever. It's just like it's downloading too slow and buffering and it's granulated, pixelated. And so I do some Google searching and I download my code and I'm like, hey, you know what? If I set my own DSCP value to EF, then the network is going to prioritize my traffic. All right, so that would be a bad actor on our network. They're going to do something malicious. So even though it's not like they're not trying to take your company down, but they are trying to mess with you a little bit. Because I've got other phones on the network that are talking at EF. And so if this switch gets traffic at EF from two different sources, what's it going to do? Well, in most cases, it's going to put it into the same queue, and my Netflix traffic is now going to get highly prioritized along with the rest of the voice traffic. So that's no good. We don't want to do that. So how do we fix this problem? Well, it's this concept of a trust boundary, and the trust boundary says this. Let's say, and I really need a larger network here. There we go. All right, so my trust boundary would say I'm going to trust this port because there's a phone there, and I'm not going to, let's just keep talking about this. I'm going to trust these ports because they're connected to switches, and I know that I've got those switches configured. And so my trust boundary at this point kind of looks like this. Whereas I do not want to trust my users. I don't want to trust anything down below my line, right? So maybe there's some other users hanging off of here. That's about the extent of the trust conversation. If I don't trust you, guess what I'm going to do? I'm going to wipe your tag as soon as I get it. So this EF gets wiped down to a 0 because that's what I've configured that switch port for. Anything coming in from the trusted interface, we're good. Now, one quick further conversation might be, well, wait a second, Jeff. I know, I got to remember now I'm on the bottom left. Is my drawing? Okay, good. My drawing's good. All right. Well, wait a second, Jeff. I know I've got a PC hanging off of my phone at work, so is that a loophole? Well, believe it or not, no, because the phones by default have an untrusted interface on like their downstream connection. So by default, it's going to wipe everything that comes into it. And this, I'll try to keep color consistency here. This switch port right here can actually be configured with a command that trusts, and then there's this additional parameter called Cisco phone. So if we have a phone on that interface, it will trust it. But if, again, I'm a bad actor, right? If I'm like, you know what, forget this. I'm going to unplug my phone and I plug myself right into that port. Oh man, well now I'm on a trusted port. That's not going to work because the switch is going to recognize, hey, there's no Cisco phone on this port anymore. Therefore, I don't trust it. Okay, so Cisco, fortunately, has put some thought into this and made it so that we can tackle most of these scenarios. All right, so that's about it from a trust perspective. That's so we spent 55 minutes on Section A. We spent 4 minutes on Section B, but that's sometimes the way it goes. Any questions on that, let me know. But yeah, configuring your trust boundary is something that you'll want to consider whenever you're deploying QoS. So on to section C. And section C is prioritization. So we already talked about this. This will be really quick too. Literally, all they want, in fact, let me just pull up the topics again. Literally all they say here, prioritization, is voice, video, and data. And we already kind of talked through this, but let's go ahead and talk through it one more time here just to be sure. So when we're talking about voice traffic is absolutely mission critical. So we're going to assign that with EF traffic. That's, again, DSCP value of 46. You're going to want to memorize that. That will definitely come up at some point on a Cisco exam. Video should, and one other thing too, from a IP precedence perspective and a COS value perspective, these would both be set to 5. All right, IP precedence is 5, COS is 5. All right, so that is voice. Video is usually going to be associated with CS4, which, again, we can think about that same concept, right, of that 8x plus 2y, where in this case y is just 0. So CS4 would be 4 times 8. So that would be a value of 32. And that, we already said common selector 4, CS4, maps to IP precedence 4, and IP precedence and class of service tend to map to each other. So this is typically what we're going to see. What was the word that they used for, it was data. All right. So they're calling it data. I tend to call it best effort. A lot of people do. So best effort. This is where we're going to see CS0, which, do the basic math, right? that decimal value would be 0, which would associate with IP precedence 0 and class of service 0. This is what they put on the blueprint. So I would have these memorized, either jot it down or grab a screenshot or what have you. This is the priority value goes up this way for sure. Now for bonus points, I did mention that VoIP control traffic is in here. Oops, voice control. So this is like, if you've ever had if you've been involved with a Cisco phone system, call manager or communications manager, that traffic, it has a value of 3. So like when it's sending the dial tone, for example, when it's connecting phones to each other, telling them how to get to the other phone they're ringing up, this would be a value of 3. So CS3, IP precedence 3, COS 3, all the way across the board. Decimal number of 24 at that point. So yes, thanks Papa House, absolutely, COS of 3. So that's a bonus points one. Another bonus points one could potentially be in here some places, and this is kind of common. I mentioned it earlier. It's called scavenger traffic. Scavenger traffic, even though we typically assign this with a CS value of 1, which, again, fill this out, right? 8, IP precedence 1, COS of 1. Scavenger traffic, even though it's rated higher from a number perspective than best effort, the purpose of it is to give us something below best effort. Because best effort is 0 and it's literally as low as we can go. If I've got traffic on the network that I want to be deprioritized, like I want that traffic, let's say it's like research or test dev or something that is like could impact the network, and I would rather have Susie and Carl be able to surf the internet because they're probably doing their jobs in surfing the internet. At least that's my hope. I'd rather them surf the internet than that traffic be prioritized over them. And so I could actually apply that CS1 tag to them, to that traffic, whatever that traffic is, and then go on to the routers. And again, because the routers 1 and 0 and 5 and 4, they mean nothing to the router until we tell it what to do with those values. And so if I get on the router and I tell it, hey, 1 is worth less than 0, the router's good with that. So there we go. So those would be the bonus points ones. The other ones would probably be the routing control traffic. And again, I didn't bring that information with me. So be sure to go Google that and make sure that, hey, you understand what network control traffic looks like. A quick search will tell you what 6 and 7 do. If you've got the official study guide, it'll fill you in on that as well, I'm sure. All right. So there we go. A few more minutes and we're done with prioritization. Shaping and policing. These I'm not gonna spend a ton of time on this just because I do want to get to there we go. Because I do want to get to congestion management because it's a lot. All right, so we're going to cover these both at the same time. So we have shaping and we have policing. These are two sides of the same coin. Okay, similar concepts, both attacking the same scenario. The scenario is this. I'm a router and I have a bunch of traffic coming in. Let's say I have 100 meg coming in. And I have a WAN circuit over here that's 10 meg. Okay? What am I to do in this scenario? And if we want to be a little more realistic, I mean, I could probably pull this out. I mean, 100 meg to 10, I mean, that's just going to be bad news, right? What if I have 15 meg coming in? What if I have 12 meg? Let's just say 12 meg. All right, and now I've got 10 out. All right, do I have to drop that 12 meg of traffic, or that extra 2 meg of traffic? Basic math says, yeah. I mean, it's got nowhere to go, right? I mean, you think about water. If it's a thick pipe and a thin pipe, then that water's just going to back out. It's got nowhere to go. But the routers do have some storage space in there. Right? I mean, it's called buffers, right? When the packet lands with the router, it can hang on to things inside the buffer for a brief time. And so the concept of shaping says I'm going to hold some of those packets back in the queue without dropping them, and I'm going to release them in hopes that I can get it all out without dropping any traffic. All right, so shaping it truly is sort of, imagine this triangle concept where I'm shaping it down. You only shape it down. You don't shape it out or shape it up. So that's the concept of shaping. The big reason why we want this concept is because of policing. Because inevitably, what's on the other side of this 10 meg link? And usually a router, and that router is owned by who? My service provider, internet service provider, WAN service provider, whomever it is. So I am sending this traffic to the ISP. Now, what's the ISP going to do if I send more traffic than it? Let's say this is actually a 100 meg Ethernet pipe circuit. This is very common, right? It's a 100 meg Ethernet connection with a 10 meg circuit. So they're telling me that I can only send 10 meg at a time, but hey, they gave me an Ethernet handoff. It's a gig. It's 100 meg, whatever it is. So it's like Big Papa House. So it's like a funnel creating the most efficient stream of data. Yes. Now, we might still have to drop traffic, and we're going to come back to that in a moment. Because in the event that I send too much information to the ISP, what's the ISP going to do? It's going to cut it off. Now, some ISPs will have burst rates and things like that. That gets a little complicated. They might say, hey, you can burst up to 15 meg or something like that. That's just saying that 12 meg would get through. As long as it's not sustained, because if the 12 meg stays, it's no longer a burst, it's sustained. So this concept is policing. The concept of policing is more of, think of a police officer and I always think of like a traffic stop officer or whatever, with the whistle in their mouth and putting the hand out like, tweet. So we've got a big stop sign here that says, okay, 12 meg is coming in to, good. All right. My face isn't in the way. Victory. All right. 12 meg is coming in, 2 meg is going to get dropped, and 10 meg is going to get through. Okay. That's policing. That's this concept of policing. Policing is usually an inbound concept. Shaping is usually an outbound concept. And like I said, they're two sides of the same coin because of this reason. So let's go back to the shaping conversation for a minute. Let's say that, okay, I've done what I can, but I have to drop traffic. I have to drop 2 meg of traffic. So does it matter? I'm gonna drink my coffee here in a moment, so I'll give you a few seconds to think about it. Does it matter, or why would it matter which router drops the traffic. Does it matter? If router A drops the traffic or router B drops the traffic, which one would it be better to drop the traffic? Which one would we not want to drop that traffic? Here's my coffee break. Think about it. That's getting colder and colder. I should probably just open up my soda water. Okay. So I see 1A come in. I assume that we want A to drop the traffic. And that is the correct answer, Panda. So the reason why we want the router A to drop the traffic is because I'm the one configuring it. And if I'm the one configuring it, I get to choose what traffic gets dropped. So if I've got voice and internet traffic going across the same circuit, I get to choose, hey, I'm just going to drop 2 meg of that internet traffic. This might be 11 meg of internet traffic and 1 meg of voice. Okay, let's just say that that's the scenario here. So 1 meg of internet traffic, 11 meg of internet traffic, 1 meg of voice. Now, if I'm in control, we're going to drop 2 meg of internet traffic, and we're not going to drop a bit of that VoIP stream. The ISP, does the ISP care? No. They just see 12 meg of traffic. They're going to drop 10 meg of traffic. 2 meg of traffic. So if all things are created equal, they're going to drop roughly, boy, now my head's breaking with the math. They're going to drop roughly like 90% of the traffic they drop will be internet traffic, but 10% will be voice, something like that. So this is why let's see here. Papa House says router A because it would be less resources upstream. Yeah, it's less about the resources and more about getting to choose the traffic type. Because that ISP is going to potentially drop my VoIP stream. So this is that is the biggest reason for shaping. Yeah, we want to not drop traffic if we can, but the bigger issue is I get to choose which traffic gets dropped. Okay, so shaping and policing. Just think of that police officer. Just think of that traffic guy, guard with the whistle and the handout or the stop sign or what have you. That's policing. Inbound, you are out of space, and then the shaping again. Think of that as that triangular shape, right? Shaping that traffic down. When you if you go on to CCNP and especially if you go on to CCIE, you're expected to understand how shaping works, and that is very complicated. Very, very complicated. But, for CCNA, we just need to understand what the concept is, we'll start there. The 2 meg. All right. So Shira has a question. The 2 meg, is it dropped completely or hold in buffer for later? So if it has the flexibility, if it has the luxury of, when we talk about congestion management, this will make more sense. But we have queues. And packets will line up in the queue ready to go. And so all we're doing in this shaping conversation is it's this guy's turn to go. Let's say we have 3 queues here. It's his turn to go, but we don't actually want to send that because we've exceeded our amount. So we're not going to send a packet. And then we come down here and can we send it now? Still no. Can we send it now? Still no. Can we send it now? Oh, yes. All right. So we send that packet. That's the concept, is we're simply not clearing it out. So when do we drop traffic? Only if a packet comes in and we don't have room for it in the queue. Then that packet or another packet would get dropped in favor of that new packet coming in. So as long as the queues don't fill up, as long as the buffers don't fill up, we're going to be fine. But as soon as the buffers fill up, that's when we start losing traffic out the backside. All right. So I believe that takes us to congestion management, and we have 15 minutes. Oh, okay. Actually, that's more than I thought we'd have. All right. So congestion management. This is a big topic, and actually, that question about dropping was a good lead in because we need to start talking about queues. Change the color here just to have some fun. What's a good color? Purple. We haven't done purple yet tonight, I don't think. Okay. So how does a router manage? Again, CCNA, the blueprint truly just says congestion management and leaves it at that. This is like the heart of how QoS works. I don't expect that Cisco is going to want us to be an expert at any one of these topics, but we should at least have a basic understanding of what we're talking about here. At the end of the day, what congestion management is saying is kind of what we just had with that scenario. We're getting a bunch of packets coming in, and we've got this concept of queues. So we've got these queues. They're called output queues. They happen usually on the output, the external facing interface, whatever that is. And so, and let me draw them slightly differently. So as I have these queues lining up here, I start filling in packets. I start filling it up with packets. So let's say I have 3 queues. How am I'm getting a little bit ahead of myself. Actually, let me not do multiple queues yet. Let's just do 1 queue. All right, let's say that I have a router. Here's my scenario. I've got a router. I've got a LAN connection here, which again is usually on the higher side. And I've got some kind of WAN circuit here, which we'll just say is, in this case, 50 meg, something like that. Okay, that's going to go over to the other router. All right, so I'm getting traffic in, and I'm going to start sending it out that WAN circuit. Now, if this is literally a physical 50 meg circuit, not really a great way of doing that, I suppose, so it's a bad example. But, if the router is incapable of sending more than 50 meg, then this is the kind of situation we want to talk about. So, and the reason I say that, by the way, and this my brain goes a few different directions on that, is that in order to get 50 meg, usually you're going to get, again, that gig Ethernet handoff, and then you're going to be responsible for making sure you don't send more than 50 across that gig. But if the router, for example, has like a T1 or a T3 coming into it, or an E1, E3, whatever, that circuit is coming in, if it's hard bound to a very specific bit rate, then we need to use these we're forced to do these queuing mechanisms. Whereas the other router, if it's a gig pipe, it's just going to send it, and that's where we need to do the shaping. All right, so that was neither here nor there. Let's just talk about this. So we have a queue. Let's just say we have 1 queue to start with. Queue, fancy word for a line, right? And so our packets are going to start lining up. And by the way, we're going to have, this is the elephant and mouse conversation that you sometimes see out of, study guides and things like that, where we have these small packets. Let's say these are the VoIP packets. Again, we'll call these the mouse packets. And then you've got maybe somebody's downloading something from the internet. And this is a big packet. So this is what we call the elephant packet. So we've got large packets and small packets in this queue. And okay, that's good, well and good. And we're going to send this packet. There's something called a scheduler here. And this scheduler from within the router is going to pick and choose. I didn't spell that right. There we go. It's going to pick and choose when to send those packets. It's going to send them as fast as it can, but it's limited by what's going on here. In our case, it's a 50 meg circuit. So it can only send packets so fast, right? It's only going to send at 50 meg. So the question, of course, is always going to be what happens when this queue gets full? So I already kind of exceeded the queue. Let's say the queue truly expands out to here. All right, so we're talking about so many kilobytes or megabytes of space, usually megabytes, etc. So we've got so many packets queued up here, and then a packet comes in. Okay, so now this packet comes in, and we don't have room for it. By default, the default behavior, we want to call it, is called tail drop. Tail drop simply means, oops, sorry, you didn't make it in. There's no room in the queue, right? It's got a Christmas season, right? There's no room left in the inn. There's no room for you. So where are you going to go? The router's going to drop that packet. That's tail drop. That's kind of the default behavior. There is a slightly better solution that we call, well, technically, first of all, it's called random early detect, RED. All right, this as a concept isn't really used anymore. We use a concept called weighted random early detect, which is with a W. But let's just talk about minus the W for a moment here. Random early detect says that, okay, whoops, I'm just gonna have to erase a few of these. All right, so random early detect says, let's just look at those words. It says early detect. Okay, so early detect says, wait a second here, we're starting to get a little full. So as this packet comes in, early detect, right, the ED part, early detection, says, oh, I'm starting to get full. I'm going to randomly decide when the next packet comes in whether it gets dropped preemptively or not. So the next packet comes in, and let's say it's an elephant, I don't know, and randomly, remember we talked about the coin flips earlier? Randomly, we're going to decide whether that packet gets to stay. If it stays, it stays. If it goes, it goes. So maybe we had to drop that one. And then another one comes in, and it's good. And then another one comes in, and that one's bad, and it gets dropped. And then another one comes in. So why do we care about it? Well, random early detect actually does smooth out internet traffic or network traffic. So there's reason in and of itself to be to use it. But where it really comes into benefit is when we add that W, that weighted random early detect. Because now we're going to give weight to the traffic type. So we might have these prioritized with our tags, and these might be those voice packets tagged with 5, and our elephants are tagged with 0. And now a weighted random early detect, our red with a W, is going to be more likely to drop 0 packets, right? The elephants is going to be more likely to drop those than it would be to drop voice packets, which again is kind of the goal, right? We want to keep the high priority traffic flowing. So this assumes a single queue. Fortunately, we don't have to worry about single queue very often. This is, well, it's not even technically the default behavior, which we're going to go into here in a moment. So Cisco, I'm doing the wrong thing here. There we go. Cisco, wait, there we go. Change color again. So Cisco said, okay, that's not a good way of doing this, really. We don't want to have just one queue, because that doesn't give you any control over the traffic, right? I mean, we saw several elephants, for example, in front of VoIP traffic. Well, VoIP traffic, okay, it's good that it made it in the queue. It's not going to get dropped. That's awesome. Unfortunately, it's not so great when that router has to sit there and churn out, even though we're talking about microseconds and nanoseconds and such. I mean, we understand that it's a small time frame from a human perspective. Excuse me. From a non-human, from a router perspective, it takes a long time to grind out a 1500 byte packet versus maybe a 50 byte voice packet, however big it is. So it would be great if we could send those small packets in front of the large packets. And with a single queue, a queue is a line, right? I mean, if there's 5 elephants in front of one voice packet, by the time it gets out, it might be too late, and that's no good. So what we have here is Cisco called this weighted fair queuing. Okay, it was kind of the early entry into more sophisticated quality of service. The concept is this: Cisco is going to, when their routers are receiving traffic, they bring traffic in, and traffic gets classified. So here's our traffic, and it first of all gets classified into something we call flows. Flows are, the idea of a flow would be, if I'm sending a file, that would be one flow. If I'm downstream, if I'm streaming Netflix, that would be another flow. If I'm playing a video game, that would be another flow. And from a technical perspective, we're looking at source and destination IP address, source and destination port, variety of other facets that would define a single flow. Because in theory, if it's supposed to be me and one computer and another machine, whatever, talking to each other. That would be a flow. That would be how we decide which traffic belongs to which flow. So first of all, we split them into flows. Then we split them into 2 different types of flows. We split them into large flows, those elephants, and small flows. Now Cisco says that most flows will be deemed small. They don't give away their secret sauce, so I don't know what the threshold is. Also, if my flows, if I'm sending traffic and it's, here's a 5 1500 byte packets, and then here's a 700 byte packet, and then here's another 1000 byte packet. Cisco's going to somehow weigh that out and average it out and figure out whether it's a large or small flow. Again, we don't really see the secret sauce of how exactly they do this. And then these get put into 2 different queues. So now we have 2 queues, which is better. And the small traffic gets prioritized over the large traffic. So if there's anything in the small traffic queue, it's going to get sent first. So whoosh, whoosh, whoosh. Those wishes are sending. That's a very meaningful sound effect. Those packets are getting sent out that interface before the large queue even gets to send one packet. So this is what we call a strict priority queue. Strict priority queues always go. If I have a packet inside this queue, it's going to go before anything else does. A strict priority queue is not always the best idea, because you could actually completely starve the other queue. If I don't know how it would happen, but if we got 10 meg of video or voice bandwidth at the same time, somehow we got up to 10 meg on a 15 meg circuit, like everything else would grind to a halt. So you have to be very careful about using strict priority queues. But weighted fair queuing does a pretty good job. Again, this is why Cisco says most traffic gets put into the small category, because you don't want to risk starving out everything else that's classified as large. All right, we've got about 4 minutes left, so we're going to go fast on this. All right, so we mentioned strict priority queue. We'll come back to strict priority queue. The concept is important. The concept is important. We're going to come back to it in a moment here. So now let's talk about the evolution of that. Now we have class-based weighted fair queuing. So we see we've got the WFQ in there for weighted fair queuing, but now it's class-based. So what's up with that? Well, class-based says I'm going to create pretty much any number of queues I darn well please. I can create as many queues as I want, because remember I mentioned that routers are software machines, and software it's not bound by the underlying hardware. Certain switches, they are, like a lot of, especially like some popular switches, the older switches like the 3560s, the 3750s, those had exactly 4 output queues. So I couldn't configure as many as I wanted. Now I drew 4 out here just because I ran out of space, but I could have 8. I can have however many queues I want. And then I can assign this traffic, I can match it based on whatever I want. Now what am I basing it on? Well, now we come full circle back to the marking category, right? So I might have a queue for EF traffic. Oops, let me just write this like over here. So now I've got EF traffic here. I've got AF11 traffic here. I've got AF21 and AF31. All right, so those are my 4 queues. As a router receives packets in and it looks at those markings, so again, keep in mind, this is the output queue. Okay, the input, you can see that, okay. The input is when it gets marked, right? And not when it gets marked, it's when it reads the markings. So it checks the marking, says, okay, you are an AF11, so as I put you into the output, under the output interface, I'm going to put you into the AF11 queue. Okay, so now we have multiple queues, and these queues are starting to build up. And class-based weighted fair queuing, essentially, before we get into the WFQ part, the class-based simply says, I'm going to do, remember this concept of the scheduler I mentioned? So this scheduler is going to send these packets at a specific rate. And typically I'm going to divvy up the bandwidth in some way. So I might say that I'm going to give 5 meg to the EF traffic, I'm going to give 10 meg to this traffic, 20 meg, I don't know, 30 meg, something like that. Okay, so I'm going to give so much bandwidth in the configuration to these queues, and the scheduler is going to make sure that we do that we accomplish it, right? That EF gets no more than 5 meg in the event of congestion. If there's no packets in any of the queues, none of this really matters. Right, we're only talking. This is why this concept of congestion management is so huge, is because once there's congestion, all of this opens up, and all of this is at play. So we take all of our same concepts and we start to apply them. If a queue gets full, we apply weighted random early detect, because we want to make sure that we're dropping traffic that comes in based on these values. So I only got so much room in the overall queue. So as the overall queue fills up, I'm going to want to drop AF3 traffic before I drop EF traffic. I definitely don't want to drop EF traffic. Okay, so weighted random early detect comes into play. We don't want to tail drop, because if we're tail dropping, now that should come to life a little bit, because remember before we only had one queue. Well, with random early detect, I actually keep my buffer open. If my overall buffer, because all of these are part of the same buffer, right? If my overall buffer is filled up to here, I will always have space to receive a new packet. And so as long as I always have space to receive a new packet, I can make a decision as to whether to keep that packet. So if a new packet comes in, it's EF, I'm keeping that packet. If that packet comes in and it's AF31, well, how full am I? Is this the last packet in the queue? Because there's a high % chance I'm just going to drop that to keep my queue open. If I'm only halfway full, there's a low % chance I'm going to drop that. That's this concept of I'm early detect, right? I want to keep my queue empty so I can always receive and choose. It's kind of like the policing concept. I want to make sure that if EF traffic comes in, I can keep it. I don't ever want to tail drop, because when I tail drop, it's just like that policing concept again. If I tail drop, it's outside of my control. I want everything to be inside of my control as much as possible. Okay. And last but not least, I'll try to squeeze it on the bottom here. There is a default class that I don't have to configure. Anything that doesn't match my criteria for the first 4 queues will get dropped off into this default class. And interestingly, if I don't use default, if I don't manually create my own default class, it's still there. And it's going to do weighted fair queuing. This same concept is going to happen within that one queue, splitting it up into large and smalls. But if I create it, then I have to manually specify to use weighted fair queuing, otherwise it's not going to do it. So it won't do this concept of splitting into large and small. I have to type the word. If you've ever seen in router configuration fair-q, that's the command, fair q. All right, so I threw that at you. Hopefully that makes sense. The last concept, I believe we're on the last concept. Let's see here, LLQ. Yeah, all right. Oops, I did the wrong thing. There we go. All right, last thing. I know we're a little bit over 2 minutes, but again, this is very important. And this is potentially the most important, because this is what Cisco likes us to deploy. Then we have this concept of low latency queuing. LLQ takes this strict priority concept, except it chops off the strict and gives me a priority queue that we call the low latency queue. And of all of my queues, guess which one I'm going to make the low latency queue? That EF queue should always be my low latency queue. I think most Cisco devices allow me to create 2 low latency queues, but then there's really no reason to. There's nothing that should be as mission critical as voice. They simply give us that option, assuming that that's still valid, because that was on the ISR Gen 2s, I believe, maybe even the Gen 3s. Either way, the low latency queue is a priority traffic in that it will always be serviced first. However, this bandwidth limitation will always be held, and it'll always be held in check by it. So if I have a packet, if I get 4 packets in here, remember my scheduler concept was that I would be taking a packet from here and a packet from here and a packet from here, and I'm going to do that at the rates of those bandwidths. So it's going to keep track of how many bandwidth is it's like speed. Like you never have a speed at any moment in time. It's always an average. It's kind of a confusing concept. And I was like, my speedometer says I'm going 50, but that's an average over the last, it took me X amount of time to get from point A to point B. So that tells me I went 50 miles an hour. Same thing with bandwidth, right? So it's taking an average over time. It's looking at that, saying, okay, I've sent it about 3 meg, 4 meg, whatever. And that schedule is going to be going through and moving packets from the queue and sending those packets. Well, the EF queue, when it becomes a low latency queue, and that, by the way, there's a key word in my configuration. The key word is right here. It's priority. So when I configure that bandwidth with the priority keyword, anytime a packet shows up in that queue, it's going to scrap its plan, whatever its plan was. Like, well, next I'm sending an AF31 packet. An EF packet just came in. I'm going to go right back up there. I'm going to send that, and then I'm going to come back down and send the AF31. It's a priority queue in that sense, but it will always do one quick check. Say, okay, 5 packets just arrived in the EF queue. So instead of sending that AF31, I'm going to go up. I'm going to clear that out. 1, 2, 3. Oh, hey, we've hit 5 meg. You two have to wait. So now I'm going to come back here, send that AF31, and then by then probably go up and clear that queue out. So it's very important because it matters a lot in that the strict priority queue could possibly starve other queues, and we do not want that. Low latency queuing is a great option because it gives us and again, it's still a priority queue. It's considered a priority queue, but it is not considered a strict priority queue. So it will always get serviced first as long as it hasn't exceeded our bandwidth limitations. Okay. I cannot believe that we actually got through all of that in an hour and 35 minutes. So I understand that was a lot of information, and good. Thank you especially for those who started at 8 o'clock and have digested this for an hour and a half. Wherever you came in, thank you for joining. I understand that was a lot of information. This video will be archived, as all of these videos are archived. Number one, it will go to my YouTube channel for permanent archival, but it will be available here on Twitch for the next 60 days. So don't hesitate to go back and just kind of go back through some of those concepts. CCNA, this is an important concept, and we absolutely need to understand this if we're expecting to pass the IC&D2. So thank you very much for joining. Hey, quick advertisement. Tomorrow at 3 p.m. Eastern, for those who are available, I am right now going through the CBT Nuggets DevNet content made by a fellow trainer of mine, Knox Hutchinson. So that content is phenomenal. It's super exciting. I just started this on Monday. It's kind of a learn-along concept. Like here, I'm teaching concepts that I know and I understand. This DevNet automation world is something that I'm trying to get more involved in. I highly encourage everybody, you included, to get involved. And so if you happen to be free, come out and watch that with me. We're watching videos, offering as much commentary as we can. I'm going to be doing the labs. It's just kind of this learn-along concept. So come out on Mondays and Wednesdays at 3 p.m. Eastern for that. Meanwhile, we'll be back here next week to wrap up IC&D2, the last section, which I believe is infrastructure maintenance. That's right. So have a great night, everyone, and we'll see you on the next stream.